Welcome back to ECE 320A. We're still in Unit 5, which means we are concerned with inverse Laplace transforms, and in this particular case, we're going to look at inverse Laplace transform with distinct roots, and those distinct roots will be real and complex. And as a reminder, you need to be finishing up your reading of Chapter 12. Homework number 5 is due, and exam number 2 is at the end of this unit. And if you have a TI calculator, an 89, or an Inspire, there are supplemental videos on how to use those to help you work through these partial fraction expansions. This video, we're working with an inverse Laplace transform with distinct roots, and let's then get that started by remembering that there are two main questions that you need to worry about right when you're starting to begin or set up an inverse Laplace transform. Question A is the transform strictly proper, which means is the denominator polynomial of order strictly more than the degree of the numerator? If it is not, then you will need to do some long division in order to obtain a remainder that has a order that is strictly less than the order of the denominator. Then once you've come up with or derived or found a strictly proper transform to work with, then you need to work or examine the denominator roots, which are actually the poles of that particular strictly proper transform. And you need to assess, are those roots distinct or repeated? And if they're distinct, then it's a little bit more straightforward to find the partial fraction expansion coefficients or the residues. If they're repeated, that will be in the next unit, and we'll talk about how to handle or what the partial fraction expansion structure looks like when we have poles that are lying on top of each other or that are repeated. This particular example that we will work through has distinct roots. And just as a reminder, there are a couple of things to keep track of. One is that the partial fraction expansion procedure can only be done with a strictly proper transform. You can perform it with an improper transform. That'll just give you a mess. And so in order to avoid going through all of that calculation and ending up with a mess, make sure that the degree of the numerator is strictly less than the degree of the denominator before you start doing a partial fraction expansion. And once you have the partial fraction expansion, that particular expression is valid for all values of s, even s going off to infinity, and that sometimes is helpful to use to try to evaluate for the residues or these partial fraction expansion coefficients. Here is our example. Again, I'm already giving you away that they have distinct roots, so we are going to be finding that we have special behavior in this denominator polynomial d of s, but it's factored into two parts right now, a linear factor or a factor that only has s to the first power, and we have in the boxed factor a quadratic. We don't yet know whether the roots of that are real and distinct or whether they are complex conjugate. But we'll find that in just a minute. But we're assuming now that the roots are distinct. What we want to do then is factor this capital F of s into terms or factors that will then allow us to identify particular expressions in the right-hand column of the Laplace transform tables and then go back into the time domain and find little f of t, which is the time domain expression for capital F of s. Our first step is really concerned with answering question A, is the transform strictly proper? That's one of the first things we need to do in working through an inverse Laplace transform problem. In this particular case, I hope that you can see that the answer is yes, because in the denominator, it should be clear that if we multiplied that all out, we have a linear factor s and a quadratic factor an s squared, which an s times an s squared gives us an s cubed. So in fact, the degree of d of s is 3, which is strictly larger than the degree of the numerator, which is 2. And that's our check on question A. Is this transform strictly proper? Yes, it is. So now we can perform the partial fraction expansion directly on f of s without doing any long division. Once we've verified that, now we can work on question B, which is let's examine the roots of the denominator and determine if those roots are distinct or, in fact, are they repeated. And the roots of d of s, or the values of s that cause d of s to equal 0, are also referred to as poles of this transform, capital F of s, because when they make the denominator vanish, they make the capital F of s blow up or go unbounded. That's where the poles come in. They're infinitely tall. So now we have pole locations or roots of d of s being the same thing, and those are the values of s that cause the denominator to equal 0 or to vanish. Or we're now looking to find values of s that cause this expression, that's the denominator expression, to equal 0. We factored it into two pieces. If we can make either of those two pieces vanish or equal 0, then the whole thing will equal 0 because these two pieces are multiplied together. Let's now look at the first piece, which is the linear factor. We want to see are there values of s, and in this case, since it's s to the first power, we're only going to find one value of s that satisfies this. If we solve that for s, we can see that s is equal to minus 1, or if we replace s with minus 1, we'll find that that parenthetical quantity is equal to 0, or our first pole or root of denominator I'll call s sub 1, and that's equal to minus 1. We've now found one factor or root of our denominator. We should be expecting 3 since it's a cubic. Let's now look at the second piece, which is written in a special factored form. We have an s plus 2, that quantity squared, plus 3, that quantity squared, equal to 0. If we work directly with that structure, let's now subtract 3 squared from both sides, and we're left with s plus 2 squared on the left. And on the right, if we take 3 squared away from 0, we have minus 3 squared. If we now take the square root of both sides, then we have s plus 2, and we have plus and minus since we're taking the square root, but now we have the square root of minus 1, which in electrical engineering we like to use j and not I. So here we're using j equaling the square root of minus 1, and we can take the square root of 3 squared, which gives us 3. Or we can now solve this for s, and we see that s is equal to minus 2 plus and minus j3. We now have 2 more roots of our denominator. We have s sub 2 is minus 2 plus j3, or a root in the second quadrant of our complex s-plane. And we have a third root, which will denote s sub 3, and that's at minus 2 minus j3, which is in the third quadrant. We now have 3 poles. We can write those or use those to write f of s in partial fraction form. a1 over the first factor, s plus 1, a sub 2 over the second factor, which is now s minus s sub 2, which if we subtract s sub 2 from s, we have plus 2 minus j3 plus a sub 3 over s minus s sub 3, which is s plus 2 plus j3. And it's very important that this particular term, the a sub 2, the partial fraction expansion coefficient, or that residue a sub 2, is associated with this factor, and this factor is actually in the second quadrant. Or this is the value of s that equals minus 2, or the value of s that causes that factor to vanish is minus 2 plus J3, which is in the second quadrant. If you put s equal to minus 2 plus J3 into that expression, it will evaluate to 0. Another way to look at these three pieces then of capital F of s to verify that in fact they do represent unique or distinct poles, if these are now S-plane plots to try to identify all three of these poles, then at minus 1 we have a pole that, or a value of s that would cause that factor to vanish. At minus 2 plus J3, if we replaced s with minus 2 plus J3 in that factor underneath a sub 2, then that denominator would vanish. And finally, the other S-plane pole location, which is now at minus 2 minus J3, if we replaced S in this factor with a value of minus 2 minus J3, that would also cause that particular factor to vanish. And we can now see that all three of those x's are in distinct locations or unique locations in the complex S-plane. And for that, we can now conclude, or from that, we can conclude that question B has been answered. Question B, remember, was is or are we in the situation where we have distinct roots? And in this case, since none of those x's are right on top of each other, then our roots are distinct. And now we can find, using whatever strategy we want, the residues or the partial fraction expansion coefficients associated with each of these three expressions by multiplying through by those factors and evaluating at the values of s that cause those factors to vanish. Let's do that for A1. A1 is just like we've done all along. We're now doing the cover-up method, but now A1 is equal to s plus 1, that factor that lives underneath A1, times the original transform, f of s, and we want to now evaluate that result at the value of s that causes that s plus 1 factor to vanish. Or now we have 2s squared plus s plus 4 all over s plus 2 minus j3 s plus 2 plus j3. And again, we're evaluating this at s equal to minus 1. We can keep that factored form alive, or we can realize that this is now the quantity s plus 2 squared minus j3 times s plus 2 plus j3 times s plus 2. Those cancel. And then we have minus j squared, which is a minus 3 squared, or which I'm trying to indicate then that we could evaluate the denominator at a value of s equal to minus 1 in this expression that contains real coefficients. Let's now continue and find what a sub 1 equals. We have the numerator evaluated at minus 1. That's 2 times minus 1 squared plus minus 1 plus 4 all over now minus 1. If we go ahead and plug in minus 1 to the factored form with the complex terms. We have minus 1 plus 2 minus j3. We have minus 1 plus 2 plus j3. But I think you can see then that that leads to, in this case, minus 1 plus 2 quantity squared plus 3 squared. The cross terms associated with the j's cancel, and so we've really just done what I've indicated we could have done in the black expression, s plus 2 quantity squared plus 3 squared. Continuing then, we end up with 2 minus 1 plus 4 in the numerator. Downstairs we have 1 squared plus 3 squared, or we now have 6 minus 1, or 5, all over 10, or a sub 1 is now 1/2. That's our first partial fraction expansion coefficient. A sub 2 is now going to be found by multiplying capital F of s by the factor underneath a sub 2, which is s plus 2 minus j3. So we now have s plus 2 minus j3 times f of s, and we are actually going to evaluate that at s equal to minus 2 plus j3, which is the value of s that causes that factor that's multiplying f of s to vanish. And we're canceling those factors in our expression so that, in fact, when we scale f of s or pre-multiply by s plus 2 minus j3, we end up with the same numerator, 2s squared plus s plus 4, all over the s plus 1 factor and the s plus 2 minus, plus j3, which is the remaining factor, and we now are evaluating this at s equal to minus 2 plus j3. Remember, this particular factor is associated with the value of s that actually causes s plus 2 minus j3. That's what we're evaluating at. We're evaluating at the value of s that causes s plus 2 minus j3, that factor, to vanish. And that's how we will now find a sub 2. A sub 2 is going to be found by replacing s everywhere with minus 2 plus j3. We now have 2 times minus 2 plus j3 quantity squared plus minus 2 plus j3 plus 4 all over minus 2 plus j3 plus 1 times minus 2 plus j3 plus 2 plus j3. We better not get a 0 in the denominator because these values of s are distinct, and we've canceled that particular factor in the denominator associated with the value of s that causes that factor to vanish. If we now do our complex number arithmetic, we will end up with, in the numerator, a value of minus 8 minus j21 all over minus 18 minus j6. And since we're dividing, a lot of times it's better to get out of the rectangular representation of those complex numbers and put it into polar form. Now we can convert that to a magnitude and an angle, and doing that in the numerator, we should end up with a number, a magnitude bigger than 21. It's now 22.47, which is the square root of 8 squared plus 21 squared. and we have an angle, and we should anticipate where that angle is. We have a negative real part and a negative imaginary part. That should give us an angle that's in the third quadrant in the complex S-plane, and in fact, we now are looking at the inverse tangent of minus 21 over minus 8, which gives us 110.8 degrees, which seems to make sense. We're now down close to minus 90, but a little bit further into the third quadrant, obviously, than minus 90. The denominator should be bigger than 18 because it's now the square root of 18 squared plus 6 squared. It gives us then a magnitude or hypotenuse of the right triangle of 18.97. And now we're minus 18 into the left half plane or into the complex plane and minus 6 in the vertical direction. Again, we're in the third quadrant. Now we're further in the real part direction than the vertical direction, or we're further in to the horizontal direction than the vertical direction, and this is now 161.6 degrees. Or a sub 2 is going to be a residue that has a magnitude that's a little bit bigger than 1, since we're dividing 22.5 by 19, and that gives us roughly 1.184. And to obtain the angle of a sub 2, we subtract a minus 161.6 from minus 110. So we're now adding 162 to minus 111, which now gives us, keeping track of the decimal or the significant digits, 50.8 degrees. Now we don't have to repeat that for a sub 3 because everything now is coming in complex conjugate pairs. Thankfully then we can say that, oh, once we found a sub 2, which a sub 2 we are associating with the pole in the second quadrant, a sub 3 is now the complex conjugate of a sub 2, or a sub 3 has exactly the same magnitude in polar form, and it has an angle that's the negative of the angle of a sub 2. And what we are going to use now is our understanding of phasors and their connection or relationship with complex exponentials, and that will allow us to more easily find the time domain expression. Recall that a phasor or a complex number that has a magnitude of 1.2 at an angle of 50.8 degrees can also be written as the same magnitude, but now it's e to the j 50.8 degrees. And so if you find the rectangular form of the left-hand side and the right-hand side, you will see that using Euler, we now have the equivalence between the left side and the right side. So writing that as a magnitude e to the j angle is okay. Or we now have our partial fraction expansion with complex residues. The A1 was 1/2. That was sitting on top of the s plus 1 factor. But the a sub 2, which was 1.184 at an angle of 50.8 degrees, that was sitting on top of the factor which would vanish when s was in the second quadrant. So this is now s plus 2 minus j3 plus a sub 3, which now has a minus 50.8 degrees, sitting on top of the factor s plus 2 plus j3. I can't emphasize this enough. This particular factor is associated with the pole in quadrant 2, and that is important for knowing what is the magnitude and angle of that residue associated with that pole. Where now, just to emphasize that visually, here's our complex S-plane, we are now talking about the pole, or the value of S, of minus 2 plus J3 that would cause that particular factor to vanish, and that's now the positive imaginary component pole, and that residue is what we have to keep track of. So that now f of t is going to be 1/2, and we now take 1 over s plus 1 back into the time domain. That's e to the minus t, or e to the minus 1t. Then we have the residue, or partial fraction expansion coefficient, a sub 2, associated with e to the, now this is s, this is the s in the second quadrant, minus 2 plus j3 t plus 1.184 at an angle of minus 50.8 degrees, associated with the pole p sub 3, which was at minus 2 minus j3 t. That's t greater than or equal to 0. And on an exam, I'm not going to be satisfied with you writing the final answer involving complex exponents and complex or phasors with angles. So I want you to now put this into something that looks more real or believable. So now let's use what we just said we recalled, which was, let's go ahead and rewrite these phasors in terms of complex exponentials. F of t now rewritten is 1/2 e to the minus t plus 1.184 e to the j 50.8 degrees, e to the minus 2t e to the j 3t. That's the first, or the second term, plus 1.184 e to the minus j 50.8 degrees, e to the minus 2t e to the minus j 3t, and again, that's t greater than or equal to 0. Now, you're not going to have to go through this laborious derivation every time, but I'm wanting you to see where it's all coming from, and I need you to pay particular attention to the sign of that angle and the location of that pole. That pole was in the second quadrant, and that's the sign of that particular angle. If it happened to be a negative, you would have to put the negative angle associated with that pole in the second quadrant. Now we can start playing with combining exponents and factoring out common values in this expression for little f of t. Little f of t is now 1/2 e to the minus t plus 1.184. That's in common with the second and third terms. E to the minus 2t is in common to both. And now we can say e to the j 3t plus 50.8 degrees plus e to the minus j 3t plus 50.8 degrees. Not doing anything fancy, just keeping track of my signs, SIGN, and the exponents. And now I'm going to be able to simplify that square bracketed piece. Everything else looks pretty good, but the square bracketed piece can be simplified by remembering Euler. Euler now says that the cosine of x is equal to, written in complex exponentials, e to the jx plus e to the minus jx over 2, which, if we now have just the numerator, this now gives rise to 2 cosine of x is equal to e to the jx plus e to the minus jx. And that is actually what we have in the square bracketed term up above. We have e to the jx, where x is 3t plus 50.8 degrees. You could write that 50.8 in radians. You would have to do that because 3 is in radians per second. You can't add and subtract those without converting one or the other to radians or degrees, but it's convention to sort of have the first piece as 3t or omega t plus and then an angle in degrees. But in calculating that with your calculator, you would definitely need to make sure that you had consistent units in that argument that I'm now labeling as x. Or we can now write f of t. The first term hasn't changed. That's 1/2 e to the minus t. But now we can collapse or rewrite the second and third terms as 1.184 e to the minus 2t, and what's in square brackets is now just 2 times the cosine of that argument in the exponent, or that's now times 2 cosine of 3t plus 50.8 degrees, and that's true for t greater than or equal to 0. Or if we wanted to clean that up a little bit, you might see this written as f of t as 1/2 e to the minus t plus 2 times 1.184, that 2 could be factored out front, e to the minus 2t cosine of 3t plus 50.8 degrees, t greater than or equal to 0. And you might see that 2 times 1.184 collapsed into one value of basically 2.3 or something close to or a little bit bigger than 2.2. Now you can see that you have a you have a decaying exponential with a exponent of -1, and you have another decaying exponential on an oscillating piece where the decaying exponential is faster. It's e to the minus 2t than the exponential e to the minus t, but that e to the minus 2t has an oscillatory component determined by a frequency of omega equal to 3 and a little offset in time associated with that angle, 50.8 degrees. Before we end this example, let's just make some observations since now we've played with distinct complex poles. One is when we were computing the partial fraction expansion, we didn't have to, it was hard enough finding a sub 2. Luckily, we don't have to do that again. We can realize that a sub 3, the residue associated with the other complex factor, that's the mirror image of the previous one that we used to find a sub 2, is just the conjugate. A sub 3 is the conjugate of a sub 2. And 2, if we now look at the inverse Laplace transform of a sub 2 over s plus alpha minus j beta, that's the factor associated with the pole in the second quadrant, that's the a sub 2, plus a sub 2 star over s plus alpha plus j beta, that's the factor associated with the pole in the third quadrant. The inverse Laplace transform of those two taken together is just 2 times the magnitude of the complex number a sub 2. A sub 2 is going to be a complex number in general. E to the minus alpha t, that's the decay, that's the real part of that complex pole, cosine, and this now oscillates at a frequency of omega equal to beta. So we have omega t or beta t plus theta degrees, where we're actually using notation saying that a sub 2 as a complex number has a magnitude a sub 2 and an angle of theta degrees. And those are actually, hopefully, consistent now with equation 64 in chapter 12. And in the 10th edition, that's on page 447. And you'll also find that in table 3 of chapter 12, which is a little bit later in the book on page 451. But I hope that now gives you some confidence in your ability to inverse Laplace transform when you have distinct poles.